I have nursery friends in the room. I know that I have greenhouse friends in the room. I know that I have grapevine friends in the room. I know that I have avocado friends in the room. I know that I have citrus friends in the room. I know I have vegetable growing friends in the room. What other kind of friends do I have in the room? Persimmon. Persimmon. What else? What else? So I need to macadamia friends in the room. I have also. And so I'm trying to give this talk that talks about a little bit about everything and everybody. And so I'm trying to shoot a little bit in the middle. And we're going to talk about the very basics of principles of irrigation and also about irrigation technology, meaning sprinklers, drippers, all the engineering parts that you use for irrigating. Please make sure from home to change your name. Make sure that your first and last name shows there, so then Mary and Tasha can give you credit. And again, thank you, Tasha. Thank you, Ariana. And thank you, Mary. You are the best. I couldn't do this without you. Thank you again. I get a lot of support from these ladies, and then I show up last minute looking wonderful, and everybody calls me Dr. Spinelli, but they do all the hard work behind the scenes. So thank you again. And also thank you to CDFA, WEDA. They give us some financial help. They bought me the tie. Not true, not true. This is my tie. But they're super helpful. They're super helpful. So again, this is the WEDA program, Water Efficiency Technical Assistant Program from CDFA. Thank you to Secretary Ross. Thank you to CDFA and everything they do. And finally, if you want to sign up for emails, you can scan this code and put your name, put your email, and you will get all my flyers with the links to Zoom, etc. Or you can also call me at 7 a.m. saying, hey, Jerry, I don't have the link to Zoom. Please forward it to me, like some of you did this morning. So how many of you, when go to Vegas, spend all night studying the book of probability like that guy does in the movie? None of us. Who cares? I just want to go to Vegas and gamble. It feels unnecessarily nerdy to think about all those numbers. How many of you think about numbers and study the book before irrigating? Who cares? Who cares? Nobody does it. I don't want to do it. It feels unnecessarily nerdy. Unnecessarily nerdy. So today, my goal is to try to push on every one of you what feels unnecessarily nerdy. So I guess you can call me an unnecessary nerd today. And we're going to try to put numbers. We're going to try to make calculations. We're going to try to use all these scary, weird formulas, not those, but close, to try to calculate quantitatively. What are we going to try to calculate quantitatively? How long I irrigate. I turn the valve on. How long should I leave it on? 1 hour, 1 minute, 5 minutes? I grew up irrigating olives for my mother, and I used to run the irrigation 5 minutes. Why 5? I don't know. Could have been 10, could have been 1, could have been 1 hour. I pulled it out of thin air. Really, and that's the way we do it. So today, hopefully, at the end of this talk, you will pull it out, not of thin air, but maybe a little bit denser air. Denser air. And it depends on the physical characteristics of the soil. It depends on the root depth for my friends that grow in the soil. And depends on the irrigation system application rate, how much water the irrigation system puts out in a minute or in 1 hour. Does it make sense? Then the next question is how often I irrigate. I irrigated today for 5 minutes. Do I need to irrigate tomorrow? Do I need to irrigate in 3 days? Do I need to irrigate next week? And it turns out that this second question doesn't depend on the soil. It depends on some weird thing that we will define that is called evapotranspiration. and it's more of a weather thing, less of a soil thing, and it's a weather thing, and also it has to do with your plants. And then we're going to talk about two more things: leaching fraction. I know my avocado friends worry about that a lot because of chlorides, and we're going to talk about distribution uniformity that nobody's worries about, and instead everybody should worry about. Any questions? So I'm from Italy. Everywhere there drives Ferrari. We export the Fiat. We export only the Fiat. We all have Ferraris. And so I went to the gas station and I said, "Oh, I have a Ferrari. It uses a lot of gas. Put a lot of gas." And the guy was, "Well, but the tank is full." And I'm like, "No. This is a Ferrari. It uses a lot of water. It uses a lot of gas. Put more gas." So the guy kept pumping gas like the tank was full, and all the gas was coming out of the Ferrari. And I was telling him, "No, this is a Ferrari. It uses a lot of gas. Keep putting gas in there." So when you irrigate for too long, when you irrigate past the capacity of your soil to hold water, this is what you're doing. And we're gonna use a lot of weird analogies today, talking about a baby that cries for food or a car that overflows with gas. But the soil is used as your tank. And we wish we had a gauge like in the car to know when the tank is full and when the tank is empty. And so we're gonna try and use that analogy. But again, how much water you apply depends on how big is your tank, and how often you apply depends on how fast your car uses gas, how fast your plant uses water. Is that clear? Any questions? Questions from home, friends? So the soil and the substrate is a porous material, meaning that it has holes. I have two sponges here, and I need two volunteers. Who's brave enough? You raise your hand. Two volunteers, no? One. So what we're gonna take these two sponges, and I cut them up so they're roughly 4 inches per side each. And 4 inches, how many centimeters are those? Sure. Yeah, so they're 10 centimeters by 10 centimeters by 10 centimeters. What's the volume of that sponge?
1,000.
1,000 milliliters, right? And here we have a graduated cylinder to measure milliliters. So this is the bet. Place your bets. When we put this sponge in the water and we make sure that it's completely saturated, and then we squish it into here, how many milliliters of water are we gonna pull out of it? Go ahead, guys.
It depends on how close I can get to dumping it in the.
Try your best. How many think that we're gonna get about half of the content in water, 50% of volumetric water content? How many say 80%? A lot more. It's almost all water. How many say 20%? How many say 5%? How many for no reason will open their mouths giving you an Okay, good. This one. How about from home? Notice that as soon as they pull the sponge out of the water, it drains. But we don't want it to drain. We want to capture all the water.
Oh,
we want to capture all the water.
Then I guess I better start over if I let it drain.
Saturate all our pores.
Did you come
with
back
water? We're trying to measure how much water fits in that sponge when it's completely full of water. Does it make sense? We call that porosity. That's the concept of porosity. That's the idea. What's the maximum amount of water that my soil can hold, my substrate can hold? Does it make sense? Who has no idea what we're doing? All right. Only me, apparently. And so the answer is, what's the answer? For the gray sponge, oh, interesting. Okay, for the gray sponge, we only got how many milliliters? 130, what's the percentage? 13%. Thank you, Dr. Tom. How about for the yellow one?
Can't read the graduations.
So I guess when I was at home, I switched it a little harder. And so I got different numbers. But the idea here, the idea still
200.
holds, right? Yes, sir.
200.
200, 20%. So when we measured the volumetric water content of these sponges had 13 and 20%. When I did it at home, I got a lot more water in them. I got 60 and 80. It turns out for those of you that were brave enough to place a bet earlier, turns out that we are on the very high side. Thank you. Particularly for substrate. For my greenhouse and nursery people, your substrate can hold a ton of water, 80%. 80% of the volume of your pot, of those dracaenas over there. Are those dracaenas? I'm kind of scared when Tony's in the room to do plant ID. 80%, thank you. 80% of the volume of that substrate can hold water. Who's blown away?
Yes.
Who thinks that is a lot? It's a lot, right? All right, very good. Anybody from home has any questions, comments? So there is a variable that we call volumetric water content, and we can say, well, when my soil is full of water, I got 60% of volumetric water content. When it dries, I get less volumetric water content. And again, it's the content of water measured volumetrically. Does it make sense? So when I'm at saturation, it's really high, and as the soil dries, it becomes smaller. And you can measure it. This is my cells with the volumetric water content sensors, and I get all these graphs. What do you think this is? Irrigation. It's an irrigation. When I irrigate, it gets a lot of water. Here it drains. This is drainage. And then this is the sun comes, the plant uses water, and then we irrigate again. And these guys are deeper, so they have less pronounced peaks associated with irrigation, right? But you can say, oh, I irrigate when I am at 25% volumetric water content, and I want to bring it up to 35%, right? So this is finally, we found some quantitative measurement that you can say, oh, my soil is wet. Oh, my soil is dry. I need to irrigate. I need to irrigate this much. Does it make sense? More or less? All right. The problem is that as soon as our friends were pulling out their sponges from the water, they would drain, right? I had to start them up again.
Yeah.
It's really difficult. It's really difficult to capture all the water because these things are trying to drain really fast. And the soil, obviously, if it's sandier, also tries to drain really fast. And our horticultural substrate likes to drain really fast. So there is some water that we call gravitational water that we cannot use. We cannot use it because as soon as we saturate the soil, all this water literally runs away from us, drains away. And so we call it gravitational water. And when it quits draining, we say that our soil is in a condition called field capacity or container capacity for my nursery people. So this is the highest, for all intents and purposes, the highest amount of water that you can use. And here I'm weighing, this is a load cell, that basically is a scale, and we have these plants, and somebody's over-irrigating them. And so this is the weight of the pot. So they apply a lot of water, and it all drains out. And this is during the day, the plants use water, and then they irrigate again in the evening. They irrigate, and all this stuff drains out. And so again, the soil, the substrate equilibrate, and then they irrigate again, right? So this is a very obvious example of somebody that is grossly over-irrigating. Does it make sense? Kind of visually, and in fact, I put this picture because you can see the substrate kind of turned into muck, and you get water coming out of those holes. And the idea is the soil behaves like a bucket with a hole. You cannot use the whole capacity because if you fill it more than that hole, it just drains. You can still use the bucket. You can still carry some water with the bucket, but not to its whole full capacity. Does it make sense? So the soil is, I think I like to think of a bucket with a hole. So at saturation, the bucket is full, then the hole starts draining, and it gets to a condition called field capacity. It's saturated at the beginning. It's saturated when it's all full. Welcome, welcome. It's saturated when it's all full, but then it drains, and when it drains, after it and the draining, it's at field capacity or at container capacity for my nursery and greenhouse friends. Does it make sense? So this is the highest amount of water that we can use. And then as the plant uses water or as water evaporates from the soil, we get to another condition, a little flakily defined, that we call permanent wilting point. There's still water in the bucket. There's still water in the soil. But these plants, for whatever reason, they're wimps and they can't use it. And greenhouse plants and ornamentals tend to be wimpier than other plants. We grow them wetter than other plants. Does it make sense? But still, your avocados or your citrus or your grapes, I guess grapes are the toughest, but still there will be in the soil some water that they cannot use. Did I convince you? So basically the quantity of water that we can use is way less than that surprisingly high amount of water that we measured at the beginning. So if you've been sleeping, if you fell asleep, this is the perfect moment to wake up and get back on the bus. Get back on the bus, because this is the point. We have something that we define available water that is in between the too wet when it rains and the too dry when plants wilt. And to make it worse, we only use a fraction of this available water. We only use half of it for reasons that I will not bore you with. But again, they have to do with the fact that plants like water. They grow faster when they're wetter. They give better yield when they're wetter. So of this available water, we only use half. Does it make sense? Did I convince you? And so you can think of a gauge, a gas gauge at field capacity is full, at permanent wilting point is empty. How much of my tank do I want to use? What fraction of my available water do I want to use? Do I stop at the gas station like my mother does when I'm at 50%? Yes, I do. Imagine a car that performs better on a full tank than it does when it's got only a quarter tank left. It goes faster for whatever reason. That's your plants. So we grow and we use only half of this available water. We deplete typically only half of the available water. And for a typical soil, back to my soil people, 50% will be solids, 50% will be preload, 50% will be porosity. So at saturation, I've got 50% volumetric water content, and then it drains, half of that porosity drains, and at field capacity, I only have 25%. I picked a loan because it looks nice, right? Everything is half than the other one. And then I use half of that 25%. So I only use 12.5% of my available tank to irrigate. Did I convince you? More or less? Did I put you to sleep? And you can look at graphs that they tell you, oh, for your loan, the permanent wilting point will be 1 inch per foot. Your field capacity will be 3 inches per foot. Sometimes they put it in inch per foot. Sometimes they put it in percentage. But that's another way to think about this idea. I have some water that is unavailable. I have some water that drains. Everything in between, I can use it. And I use half of it. Or I use 20% of it. For my substrate people, You can take a sample, put it in a Ziploc, send it to the lab, and they will give you these weird graphs with which they're trying to tell you, look, at container capacity, your soil contains 45% of water. Your substrate, I should have said. And when it's very dry, so dry that the plants can't use water anymore, it still has 22.3. And so you're like, oh, what's my available water if the difference between these two is 23%? I'm going to use half of it. I'm going to use 11%. Does that make sense? So whether it's the soil, whether it's a substrate, you can still use this framework. For the soil, if you don't know anything about it, you can use the USDA website. It's a little clunky, so I'm happy to help you with it. That is called Web Soil Survey, where you can get these weird-looking maps.
And an Asia.
Yes, sir. Yes, sir. Question from home.
Being three. And that was
Weird-looking maps of all the soils in America. It is a USDA service. And you can zoom in and look for your property. They tell you what kind of soil you have in the property. And this is more or less Bonzo.
Predict direction later. Why?
They can study different kind of soils. You can do it from home. But if you do it for all San Diego County, and also my LA friends from home do it for LA County.
That's great.
But all the available water or all the agricultural soils that you, of course, don't pick the beach, right? Like places where we grow plants, places where we have agriculture. You will find that the lowest that you can get is about 9%, 8%, which is about 1 inch per foot of available water. And the maximum that you can have is 16%, about 2 inches per foot. So you can get really deep into the details, but it boils down to your available water. If you're really lucky, you get 1 inch per foot. Sorry, lucky, you get 2 inches per foot. If you're a little less lucky, you get 1 inch per foot. Then, of course, you can say, oh, the depths of my avocados are 6 inches, 10 inches, 8 inches. I don't even know. What is it? 10, 12.
That's probably 10 inches.
10 inches. And so you can say, oh, if it was 12 inches, I would get 1 inch of water in it, of available water, right? But we said we deplete only half of it, and so you get half inch per foot or 1 inch per foot. This is a reference point. These are rules of thumb. Does it make sense? For my vegetable people, you can either dig and look for roots or use this relationship that my colleagues developed, where they say, well, depending on the days after planting, the roots keep growing, and this is the depth that they reach. And avocado, I got 8 to 12, and citrus, they can be even down to 2 feet. And I hear that grapevines, any grapevine people in the room? I hope Alicia is not listening to me, otherwise she's gonna start throwing rotten tomatoes at me. I hear, I'm not a grapevine guy. I hear that it's up to a meter, up to 3 feet, right? So obviously the root, this inch per foot, you need to relate it to the depth of your roots. Does it make sense? And my container growers people, they will do a calculation based on volume, right? They will take the percentage and they will say, oh, I've got, my pot is 2,000 milliliters, 10% of the water, I'm gonna use 200 milliliters. Does it make sense?
Yeah.
So who loves math and wants to run through some numbers?
That wasn't a vote.
Let's say that I grow lettuce in a pendulum and in bonsall. I look it up from the USDA website, 1 inch per foot. I decide to deplete only 1/3 of it. I looked up on this graph that I'm at about 1 foot of depth of my roots. And so when I irrigate, I will irrigate with 1/3 of an inch. That will wet that foot will replenish my tank at the depth of 1 foot. That's where my roots are. Does it make sense? If instead I use grapes, let's say that I'm in clay, I got 2-inch per Altamont clay that we have in the county, 2-inch per foot. We deplete half of it, so it boils down to 1 inch per foot. But I got 3 feet of rooting bands, so I apply 3 inches. Does it make sense? But then it turns out that I irrigate by drip, so I don't use the whole surface of the soil. I only wet half of that surface. Or maybe with micro sprinklers, my avocado people, they have these micro sprinklers, they don't wet the whole soil. And so let's say that I wet only 50% of my soil. So from 3 inch per feet, I go back to 1.5. When I irrigate, I apply 1.5 inch of water. Does it make sense?
Yeah.
And I don't irrigate again until that 1.5 inch is being depleted by evapotranspiration. Again, my substrate people, they look up, they send a sample of substrate, 23%, we deplete only half of it. You can measure the volume of your pot with different methods, or you can look it up on the website of the manufacturer. They will tell you, oh, 15.22 fluid ounces, welcome. Have some coffee. And then I multiply my volume, 2,000 milliliters, by my available water, 11%. And I learned that at every irrigation I apply 8 ounces. And my best nursery growers, my best greenhouse growers, at any time you talk to them and they will tell you, oh, on my 12 inches, we apply 30 ounces of water. On my 6-inch, we apply 10 ounces. They know how many ounces of water, how many fluid ounces of water they apply to each size of their containers. Does it make sense? The next problem is how long I run the water, right? Because it's not very meaningful to say, oh, Jerry, you should apply 1 inch. 1 inch what? But do I measure it with a tape measure? 1 inch of what? How do I measure what? How do I measure 1 inch of water? So there is a variable here, measure 1 inch of water. Good luck, right? So there is a variable, there is a number that we call application rate, and we express it in inch per hour. And I have an article about it, I have a website about it. I am only 1 phone call away. I sit next to my phone and waiting for you guys to call me, and nobody ever calls me. My girlfriend never calls me. You guys never call me. It's so my job is so boring because you guys don't call me. So if you don't understand, I mean all this a little bit also as a teaser. So if you don't get
Child
it,
number one.
yes, sir. Yes, sir. Questions?
Guava.
Yeah. Guava. All right. Let's add it to the list. Okay. That's weird. So for my avocado people that have an avocado orchard and they have, let's say that you have 2 micro sprinklers per tree, and I see people nodding, so I must have gotten the numbers right. And each micro sprinkler puts out 30 gallons per hour. What's your application rate? Well, you need to divide your flow rate, your total flow rate, your 60 gallons per hour. You need to divide it by your area that each tree belongs to, which is 400 square feet. And then you will get lost in the units. And so then you will call me and I tell you, oh, no, you need to multiply by 12 inch, because there is 12 inch in a foot to turn those cubic feet into gallons. And you will find that the application rate of your orchard is 24 inch per hour. And the bad news is that this is nerdy and feels overwhelming. But the good news is that it will never change. So you can get a Sharpie and write it in the wall in your bedroom. And every day you're like, oh, whoa, 0.24 inches per hour. Does it make sense?
Yeah.
And so now you know how many hours you need to run your irrigation to apply half inch. Now you learned how to measure half inch. It's 2 hours. Does it make sense? Who's bored? Okay. You can also do it at the nursery. You can look up for your particular sprinkler at 30 psi puts out 3.64 gallons per minute. Same thing, 364 gallons per minute. You divide by your spacing, 30 by 30, 900 square feet, and you get 0.39 inch per hour. And if you're not convinced, scan this code and I made an Excel spreadsheet for you. So you don't even have to worry about all those unit conversions. They're built into the formula. You just punch in the distance, the spacing, and you just punch in the gallon per minute, and you will get the application rate automatically. Who thinks that this is great? Who thinks that I'm great? Thank you, thank you. No, I don't get that very often, Fran, so thank you for raising your hand. Anybody from home, any questions? So, to sum up, the soil is your water tank. The size of your water tank is determined by your soil type, your root depth, and how much you want to deplete of that available water. And again, soil is a small tank, and shallow rooted is a small tank, and loam is a large tank, right? So the frequency of irrigation will depend on how big your tank is. But, this is a big but. The amount of weekly irrigation, the amount of monthly irrigation that your avocados will use should not depend on the soil. Because it's determined by something called evapotranspiration, which is a mostly weather variable. It depends mostly on the weather and on the canopy. Does it make sense?
Yeah.
So if you talk to a scientist, then if you talk to soil people, they'll tell you, oh, no, that's not true. But if you talk to a scientist, they will tell you, oh, your avocados are gonna use 3 feet per year, 36 inches per year. Or your avocados this week are gonna use 2 inches. And you tell them, well, how do you know? You didn't ask me if I'm on a loam or on a sand or on a clay. How do you know? And the guy says, well, it don't matter. It doesn't matter. It doesn't depend on the soil. Did I convince you? Did you buy it? I kind of never bought it as I kind of never bought it as a young student, but this is what they tell us. I promise it's in the book. So they want us to think differently, right? The soil is our tank, and the evapotranspiration is our miles per gallon. How much I use. So evapotranspiration is the process of evaporation and transpiration. They put them together because they depend on the same variable. So they say, well, it doesn't matter if you're talking about water that evaporates from the soil or water that goes through the plants and evaporates from the leaves. It's all the same stuff. It's all the same stuff because it's driven by the same variable. And so one way to manage irrigation is to say, oh, if I could calculate or estimate how much evapotranspiration I get, then I'm going to irrigate by replenishing the same quantity that evapotranspired. So my soil, yes, question.
Evapotranspiration, like, it's the evaporation from the plant, from the soil, or from both?
Both of them.
Then like each plant has its own rate of evaporation.
It does, but it gets modeled into something that they call the big leaf model, in which you consider the surface as a whole. I don't care if it's a recently seeded lettuce field that is mostly soil and it's got some little seedling of lettuce. I don't care if it's a big almond orchard in Fresno. I don't care if it's a grove, avocado grove in all. I think of the whole, I don't care if it's a lake. It could be a lake, it could be a parking lot, it could be a golf course, the turf. You model the surface, and we'll see in a minute how, thinking of the energy. And I know it sounds nerdy, but water takes a lot of energy to evaporate. That's why when you walk out of the swimming pool, your beautiful villa, and you sit there next to Naomi Campbell on the stretch on the to getting sun, and you sip on a martini. That's why if it gets windy, you feel cold, right? Because water evaporating takes energy away from you. And so we calculate, we measure evapotranspiration doing an energy balance. Did I convince you? I guess it's kind of hand waving. And the way we do this is by a system called CIMIS. How many of you use CIMIS? How many of you have heard of CIMIS before? All right. So DWR has this system. Also, thank you, DWR. Thank you, CFA. Thank you, DWR. They had this system called CIMIS, California Irrigation Management Information System or Service or something. They had all these weather stations, and they set up grass. They decided to use grass as a reference because it's easy to grow. It doesn't matter on the, you can grow it in the desert, you can grow it up in Redding, you can grow it in winter, you can grow it in summer. And they put all these weather stations that measure environmental variables that allow them to calculate evapotranspiration. Now I want you to guess, what are the variables that make weather variables that make you dry faster when you walk out of the swimming pool? Humidity,
Temperature.
wind, temperature. We're missing one, which turns out is the most important. Very good. Solar radiation. Turns out that the main driver is solar radiation, and we like to think, oh, I need to irrigate more because today is hotter. Right? We tend to relate it to air temperature. But really what drives evapotranspiration that also drives air temperature is solar radiation. Does it make sense? So they measure, where is it? This can measure solar radiation. And
But here's a half a piece of bread.
temperature and humidity. And
Like corned beef hash.
some kind of rain gauge.
Okay, yeah.
From home. You mind helping me muting people? Thank you. Does it make sense? Any questions? So you go on CIMIS and they have all these weather stations. Check this out. All over the state. You can pick your own and you will download. They give you ED0 reference evapotranspiration. If you left a bucket of water in your yard, wherever you live, in Escondido, in San Diego, in Vista, wherever you live, you leave your bucket full of water in the yard. You come back after 1 week. How much level of water went down in a week? Who wants to get half inch, 1 inch, 6 inches, an eighth of an inch? Place your bet.
How wide, how big is the bucket?
It doesn't matter, right? I'm talking about inches of depth. Right? It could be a mug, it could be a coffee mug,
1 inch.
or it could be a big pan, it could be the swimming pool, right? So 1 inch per week, per month?
Yeah, per week.
Okay. Who says more than 1 inch per week? Who says less than 1 inch per week? Who says it depends? What does it depend on mostly? Is it January or is it June, right? Which takes me to this graph. I went on CIMIS and I downloaded all the data for the 3 stations that we have in San Diego, which is the San Pasqual Valley. They call it Escondido, but it's not really. They say SPV, I guess we should get it ourselves. But so it's the San Pasqual Valley. We got Miramar at the landfill, and we got Torrey Pines. And what do you notice? We got a strong coastal influence, right? Look how much smaller. This would be four inches per month. It's about 1 inch per week, right? But look how much less you get close to the coast than you get inland, right? And this is even more detailed every week. So wherever you live, if you can relate to the climate of one of those places, I want you to look at the highest evapotranspiration that you get and the lowest evapotranspiration that you get in June, in July, in August, and in January. And so with these numbers, you will know forever what's your upper limit of water use and your lower. Does it make sense?
Yeah.
What's this? Why in March it tries to go up and then in May and in June it goes down?
Blue.
Sure. That's the one. That's the one. This is what we call June gloom and May gray. And can you tell how much strongly the effect close to the coast is? Because of the marine layer, the San Pasqual Valley, yeah, you can see it a little bit, but not really. Did I convince you?
They're asking if the orientation of your crop, like if it's north or south.
It does.
affects.
It does. That's a little bit more. That's a little bit more detailed, and it's obviously more important if you're in a hilly situation. So if you're in the valley, it doesn't really matter. Where I grew up in Italy, we are very hilly. We grow our olives in very hilly areas. So it's striking how you can get these conditions in June if you're on the northern side of the slope and the other way around. So it's a very good question, and I'm happy to follow up and to detail a little more. But last night at 11, I made this plot for my LA people, for my LA friends. Are you happy? Are you grateful? More or less. You're from LA? You're not from LA? You're from here. All right. So I got Arleta, that is in the San Fernando Valley. I got Monrovia. Look how big is Monrovia. I would have never guessed. 2 inches per week in June. Who knew this already? Right? Isn't it a lot? Eric, isn't that a lot? Monrovia?
Yeah.
It's huge. Doesn't have a big nursery over there.
Yes.
Anyway, I used to. That's right. So anyway, my friend from LA, take a picture of this or call me so I can email you this graph. That's your whole evapotranspiration throughout the year. So I convinced you already that it depends a lot on the location. And again, the UC Davis made this map with those data. And here's the trick. You use this reference evapotranspiration, which is the evapotranspiration measured over grass. That is our reference. We decided that grass is our reference. And then you adjust it up or down with this coefficient that is about your crop. So this number tells you about the weather and the location, the weather in Falcon. This other number adjusts up or down for your specific crop. And that's why we call it crop coefficient. And by multiplying the two, you get your crop evapotranspiration. That is what you're looking for. Does it make sense? And it turns out that this is not even constant. It changes over the season. Say I plant lettuce. Say I got the shipment from Brockhouse yesterday. I have all my avocado trees are this big, right? They will have a smaller crop coefficient than a 30 years old avocado orchard with really big trees that I need to climb on ladders to we still see some of those around. Does it make sense? Imagine that imagine that evapotranspiration is the MPG and we decide to take a Chevy as a reference. So then if you drive a Ferrari, you need to multiply, you get the Chevy you get the MPG of the Chevy and you multiply it by 1.2 is your crop coefficient. And if instead you drive a Fiat or a Prius, then you multiply by 0.75, right? So what we're trying to say is that grapes only use 75% of the water that grass would use in the same conditions, at the same time and the same location. Does it make sense? Do you like the nerdy, stupid example with cars?
Yes.
Okay, good.
I would-
And as I said, and as I said, the crop coefficient changes, right? This is for corn. You plant it, and then it's low, and then it grows, and then at the end it goes down again, right? So your crop coefficient is not a constant. Okay, so who wants to run some more math? We're close to the end. Let's say that it's the third week of April, and I'm in the San Pasqual Valley. So I go back here. Where do I go back? I go back here, third week in April. Escondido is the red. I'm here, 1.2. So I picked that number for the graph that Jerry made for me, because I'm lazy. I don't want to go on CMS and download all those tables, right? So I look it up on that graph, and then I get the reference evapotranspiration is 1.2, and then somebody told me that my lettuce crop coefficient is 0.8. So I multiplied the two, and now I've learned that my lettuce uses 0.96 inch per week. So now finally, we found both things, right? We know how much my tank is, how big my tank is. We calculated it earlier for my lettuce, it's a third of an inch. And then we also calculated that this week, my lettuce used about 1 inch. So my storage capacity is a third of an inch, and that week my plants use 1 inch. How many times do I irrigate for that week? 3 times, right? I need 1 inch, and my storage is a third of an inch. Did I convince you? Is anybody having a major aha moment right now?
I have a question.
Yes.
So what about a community garden that has a large variety of things growing? We have grapes and we have potted trees and we have crops. Is there more of a blanket number that we can use?
Well, so I'll deny that I've ever said this online, but just use one. If you can't, just pick grass. You know,
Oh, okay.
some things will be a little under irrigated, some things will be over irrigated. An educated guess is better than a wild ass guess, right? So still use CIMIS and use a crop coefficient of 1. Basically use the straight CIMIS data. That's what I tell to my nursery people, that I don't, what's the crop coefficient of my osteospermum? Nobody knows, we don't have it, right? And so you gotta shoot in the middle, and then in the middle is 1. But having said that, I'm happy to come visit you and nerd out on all the different crops that you have and advise accordingly.
Thank you. Yes, you're coming February 4th.
Oh, am I already? Oh, okay. No, not even know. Sounds great. I'm happy to have you there. And so the idea is, I'm driving to Portland. I'm driving to Seattle. I know that I will use 96 gallons of gas, right? That's my evapotranspiration. I know that my tank holds 33 gallons. How many times do I need to stop for between here and Portland? Right? It needs to be replenished this many times. Does it make sense? Yes. All right. So we're towards the end. There are 2 more good reasons why you need to apply more water than we just calculated. And we treat these as efficiencies. Engineers do this all the time, like, oh, I want 100 horsepower at the wheel, but the efficiency of my transmission is only 75%. So now I need 130, I need an engine that can provide 130 gallons, sorry, 130 horsepower, because I'm gonna lose some because of that efficiency. So it's the same idea here. We calculated that I need 0.96 inches of water for my plants, but you can think of them in terms of efficiencies. Don't tell my irrigation colleagues, because they'll kill me if I told you that the uniformity is an efficiency, but you can think about it in terms of efficiency. And so you divide by the distribution uniformity. And that's why agencies and folks like myself and my friends with the RCD are super into, oh, we'll come to your orchard and we'll measure distribution uniformity for free. And then we'll tell you how to improve it, right? Because a small change in this number can increase the total amount of water that you apply really strongly. So all the agencies and the water authority and DWR, et cetera, they're really into measuring distribution uniformity and improving it. The other reason is the leaching requirement or leaching fraction, that unfortunately we have crappy water down here. Comes mostly from the Colorado River. It's got a lot of chlorides, even worse if you're on a well. And so agronomically, you have to over-apply water so that additional quantity of water will drain and carry the salts away. And I see people nodding with a defeated look on their faces because it's a challenge. It's a challenge. And you use that number, you can look it up on a table, or you can talk to me offline, and we can calculate the leaching fraction, but again, boils down to something that looks similar to an efficiency. So here I was generous. Let's say that your distribution uniformity is 0.75, and let's say that your leaching fraction is 0.17. Look, my plants only needed a little shy of 1 inch, but now I need to apply 1.5 inch. So 50% more water I need to apply because of these inefficiencies, to make up for these inefficiencies. And obviously, if you had better water, if they sent us some water from the state project, from the Sacramento River, that is way better water, this number would go way down, right? You wouldn't have to apply such a large leaching fraction because you don't have to leach as many salts. Did I convince you, more or less? Okay, 4 minutes left. You can also scratch all that, forget everything you just learned. You know the movie Men in Black, that it flashes some blue line that says, oh, 1 hour, boom, and you forget everything. You know that? Yeah. So you could do that. You could do that and say, no, instead of listening to Jerry, I'm gonna listen to Gary Bender, buy some tensiometers and measure it. Who cares about what kind of soil type I have? Who cares about stimus? Who cares about the crop coefficient? Who cares about evapotranspiration? Just measure it. Just measure it. Who cares? I feed my baby when she cries. She's hungry. Ask the soil. Did I convince you? Sure. Right? But this is something really powerful, and you can use it. Some people use it in containers. The challenge is, how many of these do you put in 1 acre of those? What are they? Phosphorus? What are boxes? What are they? I got 50,000 plants in 1 acre. How many do I measure? 1, 2, 3. I want to exaggerate. 3 out of 40,000, right? So how do you convince yourself that what you're measuring is representative? How many of these tensiometers do I put next to my recently planted avocado trees? Does it make sense? So that's a really difficult question to answer. How deep do I put them? How often do I change them, right? So you get in a rabbit hole. But now we're gonna take a 5 minutes break until 10:05. I'm only allowed to give you 5 minute breaks, so use them wisely. There is some coffee. And in the meantime, you can ask questions and you can also scan this code for the evaluation. And thank you for the opportunity to serve you. And we'll see you in 5 minutes and we'll talk about irrigation technology. Thank you.